nanohub.org.
Online simulation and more for nanotechnology.
All right, we'll get started today. This is the third of the four lectures that we'll be doing on machine learning. And today I want to continue the discussion that we had in the last class. And one of the things that we are trying to do here is to explain that machine learning is a statistical approach of connecting the input variables to the output variables. And last time the input variables was number of hours studied, and the output variable was whether the student passed or failed. And the important goal here is classification, because once we do classification, then we are able to do advertisement, we are able to do recommendation and other things, and these are, as you know, very important from many business perspective and from company perspective and all. So I want to continue with that discussion, but today a little bit slightly in more detail. So if you remember the problem that we discussed, started discussing in the last class, was that if you have number of hours studied and the student, whether they passed or failed, that was sort of one input, one output type of function. And in that case, we were able to show that if you just have a single transition, a sigmoidal function can essentially help you put them in two different groups. But as soon, obviously, we are not interested in just one variable, because if it is one variable, it's like y as a function of x. X is the number of hours studied, y is so you can do a non-linear fitting. But the problem of machine learning and this big data comes because there are many inputs, and in principle, there could be many output. So here, if, for example, I'm showing you the reliability problem. In the reliability problem, there could be two input, relative humidity and temperature. Time could be an input also, but let's say we want to know at the end of 3 years, what happens to the amount of power degradation. And if it is below a certain level, then we'll say the solar farm is fine, there's no problem. And if it exceeds a certain value, same value, then we'll say it has failed. So in that sense, time, I'm not, at least in this example, not considering as an explicit variable, but it could be an explicit variable also. And what I explained in the last class was the whole point about machine learning is related to this ability to draw a line. And very briefly, I remind you that the input in here is relative humidity and temperature, two inputs. But of course, when you buy a book in Google, it could be more than several hundred million or several million inputs, because there are many variables, many products. So there can be many factors that you can put in. And the main point here is that in the last class, I explained that the circles are the ones, the farms that have failed, solar farms that have failed, physically because of the high humidity or high temperature, a bunch of them have failed. And our question, and the white ones are the ones that have survived because of the lower temperature, maybe lower humidity. And the whole point is to be able to draw a line. If you know how to draw a line, you know how to do machine learning. And this drawing a line involves, let's say, of course, you will try different ways. You will try the line this way, that way, until you are able to push most of these points on one side and most of the white points on the other side, so that misclassification is reduced. And what I explained, that if you know what this line is, if somebody told you what that line is, then that line will be given by W1RH, W2T is equal to C1. That's the equation of a straight line. And what you can do is take the temperature T and multiply with W2. So whatever is the number of variable, that will be, you will have to put it in the input layer. So in this case, I have 2. So I'll put 2. If I had 39, then I'll put 39 bubbles here. And whatever number of straight lines I have to draw to make a decision, that will be the number of bubbles in the middle. And that is called a hidden layer because you cannot really see it. What you can see is the output and input. But so here what you have to do, you have to multiply the T with W2, W1, RH. And remember this C1 will be the threshold. Remember the sigmoid has its threshold. And so the idea is that if the value is larger than this, then it will fail. If the value is smaller than that, then it will survive. So you can put, for example, any unknown point into this machine, and that will tell you that whether it has a chance of failure or success, right? So it's a very simple, and this simple function with the W1 and W2 and C1, and sigma is the width of this region. From from success to failure, the transition region is defined by sigma. And that will again, from the fitting of the curves, you will automatically get that. Now the thing is that if you looked at the previous data carefully, you may have realized that a single line may not have been sufficient. Because this single line, when I drew the single line, there were these misclassified points. And so therefore one line may not be sufficient. And if so, then I have to draw a second line. Now, of course, as soon as I draw a second line, then my prediction becomes more precise. Because previously I would have, if I had somebody ask me about a new farm in this point, I would have said that that farm will survive. But in practice, it will not. And so my prediction just became a little bit more precise by drawing a second line. But the price I have to pay as a result, first of all, let me explain what I did. So anytime you have two straight lines, you will have two bubbles. If you have 5 straight lines, you'll have 5 bubbles. And previously you have W1 and W2. Now you have W3 and W4 defining the other straight line. And so therefore what you just see, what you can just realize is that yes, things have gotten more precise. However, at the expense of additional computation, because I now have to have quote-unquote train not only W1 and W2, but I also have to play with W3 and W4 so that as a group, there's no unique solution anymore. As a group, they essentially distinguish between failure and success in a little bit more way. And then you add them and then you get the output. So that's your prediction. So now your hidden layer has two quote-unquote neurons, and this is called artificial neuron because just like a brain cell neuron, it is being connected from the previous points in some predetermined way with some specified weights. Now it turns out, of course, nobody is preventing you from drawing many lines. For example, you have a very complicated system in which the success is defined by these blue points and the green region. These are successes. And everything else is failure. Right? So therefore there are 2 islands of success and there is many islands of failure, let's say. So what you can do is that for every straight line that you want to draw, you can have a bubble. And you can add them with different weights. And you can subtract and add so that only these 2 eventually gives you an output 1. And otherwise everything gives you an output of 0. So this will be called a single hidden layer problem. This is also will be called a shallow network. And I'm going to explain a deep network in a minute. But this is a shallow network because you have only one hidden layer. And in fact, as I explained in the last class, any function that you have. So if you can think about it in 3D. So this is your x-axis and this is your y-axis. And in the third dimension, you have this blue island, z, in the z direction. And you can, of course, get any function. You can derive it by having a single layer in here. So that's how it works. This is, if you didn't know anything, you just draw a lot of straight line and that does it. In principle, you can do any of this calculation and you can see there's nothing really very sophisticated about it. Of course, you have to choose your W1 and W2, W3, W4, W5 and all those things, you'll have to play out a lot of rules. You can write a MATLAB code or you can download a code from somebody else. And this is what the commercial softwares do, like TensorFlow and other softwares that you can see that's what they do. They just vary these weights until they get the right islands specification. Now, of course, the issue is that you don't have to have one layer. You can have two hidden layers. And I want to make this distinction because very soon I will do more sophisticated things and do things in a way which is probably nobody does it in the machine learning community, but I'll try to explain that a little bit more. So what is the point? Why do you want to, if you could do everything with layer 1, why do you want to go to layer 2? The reason you do it this way is because let's say you have these 2 points. So you can have a structure which is like these 2 lines and you can make them a unit. And then you can have these 2 points and then make them another unit and then combine the units. So instead of sort of drawing a lot of straight line defining an island, you can do it hierarchically. You define one region, for example, this in here, all these regions are success and all these regions are failure, let's say. You define another one where only on the right hand side everything is success and then everything on the left hand side is failure, and then you combine them in the second layer. So that way you can hierarchically build up the same function, but you do it step by step. It is like, let's say you can use a lot of lines to draw a complicated polygon, or you first can make a triangle and then can sum up a bunch of triangles to make a polygon. So therefore, you will want these things many layers. Anytime you want to develop, you want to build one top of each other. And that's how all this handwriting and all algorithms that are done, that is exactly how they are done. This is a bunch of straight lines. So you define the straight line, you get one. Then you define another region. And by defining these regions, you eventually can see whether it's a picture of a dog or a picture of a cat or whether it's a picture of you. That is how it is done. It is done on a hierarchical basis by combining polygons of different sort. So when you do handwriting recognition, this is a very sort of widely used problem set. And in that case, again, what you do is that if you are drawing a 1, there is 2 segments, let's say, of equal straight lines. If you are doing a 4, so you build it up hierarchically. And that's how you can do the system. So all has to do, in a few minutes I'm going to show about computational efficiency. Because in principle, you could have done it with a single layer and then essentially have done this job altogether, right? So let me explain to you why it takes so long to train a network, and that will immediately explain how you can sort of think it more systematically using Karnaugh map and other things. So let me start with this. This is an example I took from a web page, and if I walk through this one, you can. Very well done. So I will show you how this is done. Remember how we fit a straight line on a normal XY curve. We try to fit this straight line so the error is minimized. And in here, we don't think about error per se. What we do here is loss function, the misclassified ones. That's what we care about. So let's think about this example. So this example has 2 inputs. 0.05 and 0.1. Last time we had, for example, temperature and humidity. In this particular case, it is something of that variable of that sort, 2 variable, x1, x2. And output is 0.01 and 0.99. So previously we had one output, pass fail, or success or failure. But in this case, they have 2 output. And many times if you want to do a sum of a bit of binary. So you have a sum and you have a carry. So there's no reason that why you have to have a single output. You can have 1, 2, 3, 5, whatever number of outputs. So let's say that I have this value 0.05 and 0.1, and my training data says that I have to adjust the weights in such a way so that the output becomes 0.01 and 0.99. That's my goal. That's my training data. Remember, in the previous case, I had many training data. Each point on the success and failure was one training data. Here I have just one training data, not many. And let's see how I can satisfy the training data. So what you do, you start with a guess. Like any good people, you start with a guess. And here the guess is 0.15, 0.2, 0.25, 0.3, 0.4, 0.45, 0.5, 0.55. You know, you're guessing. So put something over there. And this is where the machine learning becomes very difficult, because they start with a random guess. So if you have some good guess, life is good. But if you don't, this is where you start. Okay. So now let's evaluate this function. I will just not show you too many, but so that you get the feel, but you can sit down and do it. For example, what is the output of H1? What is that output? Output is, there is a one typo in here, so therefore, but I'll point that out. What is the output? 0.15 is this. Remember, W1, X1, W2, X2, we have to add it up. So 0.15 and 0.05. 0.05, this 0.05. So that's one value. And then I have 0.1, and I should have multiplied with 0.25. So I have written it 0.2, but I should have multiplied 0.25. And the C, the value, remember that there was this intercept C. So that C is written here as 0.35. So I add 0.35 multiplied by 1. Now there is a sign thing. Previously I was writing C1 on the right hand side, but here it's written on the left hand side. You get the idea. So you add it up. If you add it up, then the value you get is 0.3775. That will be the sort of the input to the system. But that's not will be the output. The output would be the sigmoid function. Do you remember what it was? 1 plus e to the power, that z, and the z is the whole thing. So you have 0.3375, and this is what it did. The sigmoid function did that. If you had a tan hyperbolic, you would have done tan hyperbolic here. So you put that in. So the output of this at this point becomes 0.59. Similarly, you can get the output of this, and which is output of H2. Where is output of H2? Did I write it somewhere? Yeah, out H2. Similarly, let's say you do the calculation in here, you will have 0.5968, whatever. You will have all those numbers, and then you go one more level, and that will give you out of 1, and similarly, you will get out of 2. That will what we'll get. Do you see that these two are completely wrong? Why? Because it is 0.75 is output, but didn't I want my output to be 0.01? And this one, my output is 0.77, but I wanted my output to be 0.99. So I'm completely wrong. So what I have to do is to readjust this W1, W2 again until it gets there. How wrong am I? So I can calculate the error or the loss function. You can see that 0.01 is what I want it to be, but I got 0.75. So that will be 1. And the error of 2 is similarly, I want it to be at 0.99, but I am at 0.77. So if you square that, you will get that. And the total error, this is the loss function, that is how much error I have. So I have to do something. So what can I do? I can just randomly do W1, W2, randomly throw things and until I hit it. But that you can see will take me forever. And I am never guaranteed that. So this is where the computer scientists come in. This is their job. They are not doing any sophisticated physics. They don't know physics. Oh, I should say that. They know physics, but they don't know. They are not really care. That's not their care. Their care is how to find it. So let me quickly show you how they would do it. I'm going to show you a little bit, but this example is detailed enough so that you can go in and do it yourself. For example, so what they do is essentially see that if you change one of these coefficients, then if you change one of these coefficients, how would the output change? And then if the output is changing in the right direction, that is the error is becoming smaller, they will accept it. If the output is changing in the wrong direction, then they will apply a negative value and then they'll force it to go in the negative direction. It's like taking a derivative. If the derivative is, you are taking a derivative going in the right direction, then you accept it. Otherwise, you go in the opposite direction. And so the whole thing that is done in here, I will not go through this in detail, but the whole thing that is being done here is sort of successive derivatives, partial derivatives. So you ask this question, if I change W1, how does my error change? If I change W2, how does my error change? And thereby I change this a little bit. And what you do, the reason it's called backpropagation, you first do layer 2, then you do layer 1, and then you go back to layer 1, layer 2, and then you do layer 1. So therefore, you're backpropagating. And if you do it a few times, just like any normal numerical iteration, you will get the answer. And every time you do the updates, it's called an epo, right? So therefore, this is a generation, as if one generation, it has evolved one generation towards the right answer. It turns out in the beginning, the error doesn't really move very much. After doing all this calculation of taking partial derivatives of the output with respect to W1 and writing it as fractional derivatives, sequential chain rule and all, eventually you get a number, but you see the old error in the beginning of random things that I chose versus with this one, it has not really changed very much. And often you will see it will take 10,000 iterations before it can get there. But the computers are so fast that the 10,000 iteration may just take a fraction of a second, right? So that's why you needed modern computers in order for this thing to succeed. Yes?
Is there a sequence of going back, in a sense?
Sequence meaning?
Is there a particular prescription of to go back in the same branch, or do you?
I will tell you. So what is always done is that you always start with this first. So you say that if I change W5, how would the error change? And then you adjust this one and this one. So you always start with this last row. Then you fix this one, keeping these on fixed. You don't touch them anymore. You change this one. And remember, in many machine learning algorithms, this may be 152 layers that you have to go back, right? So therefore, it takes even one iteration takes a lot of time. And then you check what the error is. And then you're going to again start from, Yes?
So if you have multiple layers, does this backpropagation become easier as compared to if you have a single layer and all of the functions on it?
So this is something I'm going to tell you, what I'm going to explain to you in a single layer. Let me get there. I will. This is a very important point, that the depth of the network versus the width of the network. I said that both can be represent the same function. Which one is more efficient is something that we'll discuss in a few minutes. But the idea is clear, right? So you do one set of backpropagation, fix the coefficients, do a forward sweep, get a new error. The new error is still not good enough. Do another set of backpropagation, get the values, and then evaluate a forward function. So that's how you will iterate. So you see, there's nothing to it, right? It's very simple. And for example, after 10,000 iteration, what you find that, let's say, the second iteration is like that, but after 10,000 of iterations, you find that the coefficients are, even in the first one, the coefficients are changing a little bit. Your error has reduced a little bit. And then eventually in the final one, you will get all your errors in the right value, and you will get within 1% of the final value. Now, this is just one sample. Think about it. If you had to train, let's say you have 10,000 data points, and you had to do this over and over again so that it represents, on average, the 10,000 points reasonably well. Hence the computation. So let me explain this notion of deep versus shallow by using what I know as an electrical engineer. Because only thing I know well is how to do digital design, right? Because as undergraduate electrical engineers, everybody will learn all those things. So let's say I want to give you an analogy, because I will solve a problem here and then I will explain to you how to think about machine learning and the deep versus shallow network. Let us consider a situation where I have 3 digital input A, B and C, and the output is Y. And as you may have realized that you can have 8 combinations for A and B and C, and let's say there's some random combination of Y, depending on what you are doing. So in some way, this will be your, what will these things be? It will be the output layer of a machine learning thing, right? And what will be this? These will be input layers of a machine learning thing. Here, the machine is a digital machine, because it can just have 0 and 1, unlike the temperature, which is analog machine. Analog machine may have a fractional value. Remember, the last one, it has 0.05, whatever. But in digital, you have only 0 and 1. But remember, in the CMOS circuit, it's never 0 and 1. When you're propagating from gate to gate, that's also analog. You're just converting it 0, 1 on every layer. So this is not exactly digital when you actually implement it. But let it be. So let's say I have A and B, and I'm being asked to define this function f that will connect ABC to Y. How would you do that? You generally can do it in either of the 2 ways. You can do it as a sum of products, which is you just check everywhere that thing is 1, everywhere the thing is 1, and then you write the corresponding expression. For example, this is 1, so therefore it will be A bar, because it's 0, so it's A bar, B and C, that's your first term. And then there are 3 terms that are 1. You can easily convince yourself that this would be your network. Y has that particular expression. If this is not it's something that you can also see it in the Karnaugh map in the in YouTube or other things if it's not clear, but you get the idea that if you may have seen this before. And then if you want to do a Karnaugh map, how do you do that? If it's a 3-input Karnaugh map, then what you do is generally you write A in here on this side and B and C over there. And then you just copy this table. Everywhere Y is 0, for example, A, B and C. A, B and C. So this thing is 0, right? Where have you seen this before? This type of thing before? Design of experiments. Do you remember in the design of experiments we were looking at various combination of factors and all, orthogonality and all, right? So these are all connected that way also. So I have written this once, and you remember that there are, this is interesting. I may have made one mistake here because I see 3 ones, but I have 4 ones here. So I may have made a mistake. Huh?
It should be 1, 1, 1, 1, 1.
You are missing one, because you should have 8 rows, you have 7 rows in the input.
Oh, yeah. Oh, sorry. So this is 1, 1, 1, 1, 1. Excellent. And so that's 1. So I should really have, in that case, a 4th term. I should have a 4th term. But you get the idea. Thanks. But yeah, the Karnaugh map is actually, this is a special way of writing. If you don't remember that A has to be 0 and 1. These are the things that you can write. But when you're writing B and C, you have to never flip it beyond more than 1 bit. So 0, 0 is fine. Next one is 0, 1. But you cannot write 1, 0 after that. Because 1, 0 will be involved 2 flipping, but you have to write 1, 1, so that because then you change 1 bit and then you have to write 1, 0. So this is the rule by which the Karnaugh map works. And you also know, I hope, that you only have to worry about the ones and you have to circle them at the powers of 2. So you can do 2 or you can do 4 or you can do 8, but you cannot do 3. Or 7, you cannot do that. So for example, I have circled it in here. This is 1. And then I have circled it in here. That's another one. And I have circled it in here. That's the 3rd one. I cannot circle it like that because that would involve 3 of them. And the rule is that anytime you are writing this, you have to only worry about you will not worry about the terms which is flipping. So for example, in here, what is flipping? A is flipping between 0 and 1. So I will not care about A anymore. So what should I write? I should write BC. BC is what I care about. And then similarly for this one. For this one, A is fine. A is not flipping. So I have A. But between this, B is flipping from 0 and 1. So therefore, I don't care about B. What do I care about? C. C is not flipping. So that's that. And I leave you as an exercise that you just look at the last one and it will be AB. And the point is that immediately this process simplifies your system, because I should have written another one which would have made it a little bit more sophisticated. So you can see that there will be many inputs, and how many weights now you have to calculate. Do you remember that there is a W1, W2, W3, W4, W5, W6? So you can immediately see that if you didn't compress this way, then you would have had many coefficients to fix. In this particular case, you have only two, 1 and -1. But in general, for machine learning, you would have to have done more. And by doing this, you considerably simplify the network, because you just now have two of them. And as the system gets more and more sophisticated, you will see that this one will grow. Shallow network is essentially a sum of products. So therefore, it will go as 2 to the power n. And that's why people don't use shallow network, because there are just too many weights. You can see that by going to quote-unquote deep network, here is just one layer, it will essentially reduce the number of coefficients that you have to train and dramatically reduce the computation time, right? By the way, and one thing, as you know, in digital design, that in AND, OR, and NOT gates, if you know these three things, then if you have these three gates, you can design everything. You don't need anything else, right? Or you can have just NOT gate, or you can have NOR gates. You know that. It turns out that every bubble in machine learning is actually can also be viewed as an AND gate, OR gate, or a NOT gate. For example, let's say you have temperature and relative humidity, A and B, and let's say both are present. The weight W1 and W2 are 1 and 1, let's say. If you want this to be that when both of them are present, the things succeed, let's say, then in that case, what do you have to do? You have to just sum these two and make the threshold a little less, so that only when they are simultaneously present, then output will be 1. And if one of them is present, the other one is not, you can see the output sum will be 1, and that will never be able to flip that thing. So therefore, anytime you want to have an AND gate, you will put the threshold slightly lower compared to the sum of the inputs that will come. Similarly, if you want to have a OR gate, what do? You only when you have both 0, 0, it will not flip. But if any one of them comes, then it will flip. And so that's how you make an OR gate, making the threshold as larger than the lowest weight that you have. And finally, if you want a NOT gate, you just simply flip this thing, but flipping itself will not do. You will also have to change the threshold by 0.5. So this is because it's a sigmoid function. If you wanted to have tan hyperbolic, then you would not have to need to shift the function. Bottom line, that the nodes that we saw in that network is actually a little AND gate. It was not, there's nothing written as AND gate, little OR gate and little NAND gate all sitting there. How did I have NOT gate? Anytime the coefficient W4, let's say, was -1. That means it was sort of inverting whatever came out, inverting the thing. So you can immediately see that, for example, you cannot represent an XOR gate by a single layer, one layer. And let me not go through that. It's again the same thing. A and B is the input. And what is XOR? XOR is when one is present, it is 1. But when they are both present, then it is 0. Right? Both 0, 0 and both ones are also 0. And only when they have different opinions, then you give them full credit. Right? So that's what these things are. And as you know that you can again write this function. You can write A bar B, which is A bar B, and you can write A B bar. That's your expression, and then you can rewrite it. It's De Morgan's rules. You can rewrite it. And that's how you get this one. So you have A dot B, and that makes it NAND, and then A or B, output of that is ANDed together. You can see this has two hidden layers from the input to the output. Now, if you wanted to do a sum of the product, you could just have done it just in a single layer. Just add them all up with the OR gate. So, the point is that therefore, you can do any design if you want. First, you can, if you want to have a XOR implementation by machine learning, all you have to do is to make sure that, for example, this is an OR gate, right? Remember the first one was supposed to be an OR gate? The previous one, for example, this was supposed to be an OR gate, right? And we know what the rule for OR gate is. What is the rules for OR gate? That this threshold, this is what I did in the last one, but these two are equivalent. Let me show you. This line and this line, these are the same gates, but implemented in two different ways. So here is the one that we just saw. So you do a NAND, this is a NAND, and you do 0.6 and 0.6, and only when both of them are present, then this one comes out, and you have a -2, that gives you the NAND function, because this is AND, and then you are inverted in the NAND. And similarly, you can see, you can check it out that this is AND and this is not. So therefore, these two machines will essentially give you the same result. That's why in the machine learning community, there are many different configurations that can give you the same answer. Yes?
I don't understand why you have 0.6 or 1.1.
Which is?
The weight.
Over the
No, I'm just showing you an example. Just an example that if the weight were W1 and W2, if you want to have a OR function, then you have a 1. But if you put numbers in here, for example, if you put 1, 1, you will see the XOR function will come out of this. Right? So this is what makes things interesting, because you see that if you have a 4 input, I'm written it in the Karnaugh map from, and you have so many ones. How many? 7 ones. So how many points would you need? You'd need 7 hidden layers. And how many input do you have? A, B, and C, D. So you have 4. And everything has to be connected to everything. I got tired, so I did not connect them. But you saw that everything has to be connected to everything. This is the problem of shallow networks, that you need too many connections and too much training in a shallow network. On the other hand, if you did the Karnaugh map, this is your corresponding one. All these networks that you need, you still have ABCD, A, B, C, D, yes. But now you have only three nodes instead of having 7 nodes. Remember previously it's like instead of having 7 straight lines chopping the function, now you need just 3 to do the same thing. And you can immediately see the number of coefficients. Previously it would have been 14. Now it's 6. And so therefore this system will converge much more faster. But of course then the problem is that you have to also have weights for this one. So that will give you some extra, because now as you are getting deeper, then you will actually have a few more weights. But it is much smaller growth in terms of number of unknown coefficients compared to the other one. So there is a famous theorem by Shannon which says that if you have the n number of inputs here, for example 4, then what is the smallest amount of node that you can use in order to connect it to the other side. I just want to give you a big picture idea, right? And then if you do the homework with the TensorFlow, these things you will immediately become clear that what it means. And you will be able to see then at that time that this is AND gate, that's OR gate, and so on and so forth. So let me stop here in terms of, so I tried to explain in this section, in the section 4, is that machine learning involves a bunch of bubbles, and each bubble is really a straight line. And you need many bubbles, because any time you have a complex region in a many-dimensional space, you have to think about a circle. If you had to do a circle, that's one thing. But if you had to draw it as a segment of straight lines, you will need many, many straight lines to do it. That's why it's so difficult. I mean, it gets very big very quickly. Therefore, just like singular value decomposition was not fast enough, many times this classical form of machine learning is still not fast enough. So then what people do? Because you have to do backpropagation, you have to solve all these straight lines and all, you want to do something simpler. So then I want to show you a few of these things. You will choose what you need depending on the application you have. So you remember that one technique I want to tell you about is unsupervised k-mean clustering. This is very popular, but it will give you an idea. Supervised, you remember, right? These students were failing. These students were passing. The blue students were passing and the red students were failing. And I knew who passed and who failed. But often, let's say the university is very careful. They don't want you to know who passed and who failed, but you still want to know that whether there are two groups of students and whom you want to admit. But they didn't tell you anything about the student. So that's unsupervised, or unlabeled. There's no label, but you have a bunch of points. And only points you have is the input. You don't have any output. So now what do you do? So now what you do is try to see whether there is any pattern in the data. Now, because you don't know anything, you can say, well, it looks like that these students are probably similar. And these students are probably similar. Maybe there is another group in here. So you have to decide how many groups you want. And k-mean clustering means how many groups you want. So if these people like coffee, maybe this person likes coffee. So this is what you are trying to do. You are not trying to get exactly the cutoff at which there is a transition. That's not the goal. You're just trying to get some basic idea. And in experiments and in many other cases, finding this pattern, that's what your advisors often do. They have enough experience so that they look at a physics problem and they try to see whether there's a pattern in there. They don't know the physics. So they are trying to see whether this class and that class, is there some difference. So how would you do that? It turns out there's a beautiful algorithm here. So what you do, you take two of these points, any two you like. You take as 2 points and say that that's the centroid or group leader of that group. Now obviously it's wrong, right? Because you thought that this would be a group, but you have chosen one in here. But it's okay. Because in many dimensional space, you cannot go in and see the pattern in the data. In 150 dimensions, you don't even know that this group or that group. So you have to let the machine find out the group. And so how do you do that? So let's say you take 2 points. And then what you do from these 2 points, you find out the distance of everybody. Everybody. So therefore, what is the distance? 0. You have some distance here, you have some distance here, you have some distance here, and write it as a column. Then from the other one, you also write the same distances from everybody. Then you have 2 columns, one column distance, another column distance, and whoever it's closest to, it goes to that group. For example, this one, there is a distance from here to here and distance from here to here. So therefore, it will go to the blue group. And this one, the red person only will have these 2 in its column, because everything else, the blue is closer. And so therefore, all these points will sort of become blue temporarily, and all this point will become temporarily red. So the ones that have become blue, you have to get their average, or you can get their mean, the median. But generally, average is done. So as soon as you try to get the average, because that's what you are trying to get, the centroid, what will happen? The blue point will run to the middle. And these red points will run to the middle of its own group. But you can see that what's going to happen now. What's going to happen is that the second the blue has gone here, all these points which were sort of farther out from here, they will now begin to join the red group, right? So they will join the red group. So now they will join the red group. And then you do this until this one stabilizes. That is, this point, this centroid points, the captain of the team is not changing the group anymore. That's it. So that is called K-mean clustering. You understand K-mean here is, what is K? 2. Because I decided that I wanted to do 2. That's why it's 2. And mean, of course, you are calculating mean and you are doing clustering. So therefore, it is called K-mean clustering, a very powerful algorithm. Now you could say that, no, I want to do 3. If you wanted to do 3, fine. If you will start with 3 and then it will divide it into 3. It turns out that in higher dimensional space, in lower dimension it's no problem. I wrote a little code on the other day, just a few minutes it takes. But the thing is that in higher dimensional space, you need other methods because sometimes the clustering is not very good. So there are other ones which clusters things a little better. So you can do 3-mean cluster and all. But the problem is that sometimes, this is what I was saying, that sometimes the K-mean clustering can take in points as its neighbor, because it's all neighbor based, which really in principle should really belong to the other group. And so there are other algorithms which can do a better job, right? Now this is how the recommendation system works, because if all these people in Amazon are buying books, then if this guy bought a book and you are searching and they find you in which group you belong, they also recommend you that book or that they are interested in. This you can see, no backpropagation, no straight lines, nothing. And so therefore this would be extra fast. What is wrong? Well, what's wrong is some of the students actually passed and you made them fail. So therefore in the boundaries, you will be making many mistakes, but all you care about is their money. So therefore, you don't worry too much about in the boundary who is sitting there, right? It turns out that all things, I'll just show you 2 slides and I will wrap it up. The point is that it turns out that this is classical machine learning is generally very energy intensive, very slow in that way. So therefore, people are reusing nanophotonic circuits, and in the nanophotonic circuits where many of these training can be done much more faster. So I have done this. This paper is very good, and the idea is that all this layer 1, layer 2, you can essentially implement them all in optical components. And the key thing is that single value decomposition. You see every layer, this vector, you can represent it as a singular value, but this is a singular value decomposition which is different from the previous one, but you can always do that. And U and V, you can represent it with optical elements, and this is with nonlinear optical elements you can do that. And this is a example that recently people have done that it has been implemented and it's much faster. Quantum machine learning is another emerging area, again for classification performance. So I hope I have explained to you the multi-layer and multi-input networks. You can handle very complex systems because it doesn't rely on physics, but you can make very good prediction. And digital mapping onto digital system makes things much more understandable, because without it, it just looks like a random thing that's happening without anything. And then there are many machine learning tools. In your notes, you will see that there are also 2 other things that I have included, but I didn't have time to go through them. This is random forest methodology and all, but I think you don't need to know everything. What you need to know is the general concept, and then later on you can teach yourself. There are a set of references. I hope you will look at those references and then try to answer.